So for this last video, I want to combine the delta method with the Fisher information, so the last two videos, and tackle a example from the book. I'll be doing example 9.25. Bit of prereq knowledge. Actually, a lot of prereq knowledge. If theta hat MLE is the MLE estimate for theta, then we know that G of theta hat MLE is the MLE estimate for G of theta. So you can combine this with the delta method. This is the theorem right above example 9.25 in the book that I'm getting this from. That we have G of theta hat MLE minus G of theta over standard error of G of theta hat converges in distribution to a normal 0-1 distribution. Note that standard error of x is equal to 1 over square root of n times I1 of x. Note this sub 1, it means that it, instead of in the last example where we had I sub n of x, meaning that we had a sample of size n, we have a sample of size 1. Or, equivalently to this, we have G of theta hat MLE minus G of theta over absolute value of G prime of theta hat, standard error of theta hat, converges in distribution to a normal 0-1 distribution. Okay, so now using this to take on example 925, we have xi's are ID Bernoulli random variables, right? From the last example, or from the last video, we know that in of p is equal to, just want to make sure I wrote that down, yeah, n over p times 1 minus p. So I1 of p is equal to 1 over p times 1 minus p. So plugging that into what we just wrote the standard error as, standard error for p hat is equal to square root of p hat times 1 minus p hat over n, or standard error of G of p hat is equal to absolute value of G prime of p hat times standard error of p hat is equal to absolute value of 1 over p hat times 1 minus p hat times square root of p hat 1 minus p hat all over n, which is equal to 1 over p hat 1 minus p hat n. Now we can use this to make a 95% confidence interval, right? That's the whole point. Yes, so we want to make the 95% confidence interval, right? So we would have we know that the MLE, okay, so we want to make the confidence interval, just looking at this example, for our function, or g of theta hat MLE, g of theta, or g of x is equal to 1 over x time, gosh, I cannot write today. G of x is equal to log of x over 1 minus x, right? So then the MLE of, so the MLE of g of theta is equal to g of theta hat MLE, which is equal to ln of p hat over 1 minus p hat, right? Because you can just plug that in you can plug the MLE for p in where p goes. And the confidence interval is this MLE, or ln of p hat over 1 minus p hat, plus or minus approximately 2, because it's an approximate 95% confidence interval, over square root of p hat 1 minus p hat n. That's the appeal of using the standard error.